Wow.
Yeah.
Okay. All right, WebEx is still acting funky. All right, well, this is the end. Now, as far as basically almost everyone who's electing to take the oral final, and trying to get those, now getting scheduling requests. Did you go with the 9th? No.
I did say 9.
Yes.
But I told you that by next week I will tell you if I could prepone.
Okay, so you don't know yet.
So I mean, how much I'll be prepared by next week.
Oh, okay.
But otherwise, 9.
Right. Okay. So just get back to me. Okay. Anyway, I have 2 out of 5 people scheduled on the 9th. So it's need to hear from everyone else. Okay. So and doing encoding. This topic is certainly highly relevant to that. But those who take the oral, I may ask some questions about boundary value problems. We saw a shooting method already, and now this is the other approach that I'll talk about. That is using finite differences. So, to refresh your memory, this is a problem that we're considering. So we have a second order ODE on the bounded interval AB. That could be linear or nonlinear. And then we have these boundary conditions that the solution must equal alpha at x equals A and beta at x equals B. So what we do is, since the right-hand side is a function of x, y, and y prime, and then we have y double prime on the left side, we approximate this ODE by replacing any derivative, so any occurrence of y prime over here, and this occurrence of y double prime over here, with finite difference formulas. And I covered those last semester. So it's in section 9.1. And there's different formulas that we can use. So we're just using the simplest formulas that have high order accuracy. So if we want to solve for y at n interior points, so each yi is an approximation of the exact solution at xi, and the xi's are these equally spaced points in the interval AB. So if I let I go from 1 to n, and I use this spacing, so as before, the interval AB is divided into n plus 1 subintervals of equal width, then these points are equally spaced points that lie within the interior of AB. So the boundary points are excluded from this set. So really what I'm doing is I'm discretizing this ODE. And here are my unknowns now. So instead of solving for a function y of x, I'm solving for a value y of x at these n equally spaced points. So in the ODE, the first derivative, wherever it appears on the right side, is the argument that f is replaced by this center difference, which is second order accurate, that this is the error formula. And then y double prime on the left side is also replaced by a center difference formula, this formula, that is also second order accurate. All right. So when that happens, the ODE leads to this system of n equations and n unknowns, or y values. So here we have our approximate y double prime minus f of x, y, and our approximate y prime is equal to 0. So now it all boils down to solving this system of equations by whatever means. And how that would be done depends on whether the system of equations is linear or nonlinear, or based on whether the ODE is linear or nonlinear. Now, for convenience, we're looking at solving for y1, y2 up to yn. So y0 is the left boundary value, alpha, and then yn plus 1 is the right boundary value, beta. And my interior points, as I mentioned, are x1, x2 up to xn. x0 is the left boundary point A, and xn plus 1 is the right boundary point B. So this will come in handy for using these equations when we near boundary points. Okay. Now, I'll talk a little bit about convergence analysis. So with initial value problems, time stepping, we had the notions of consistency, stability, and convergence. So those concepts are important here. They just have to be defined appropriately for this kind of problem. So we still have the notion of local truncation error, as defined very similarly as for initial value problems, where you substitute the exact solution into the numerical method. So here, this system of equations that arose from the ODE, we now substitute the exact solution into that. And then we try to simplify this as much as we can, also using Taylor expansion as needed, to get an expression for the local truncation error, so we can determine, for instance, the order of accuracy of the method, or determine is the method consistent. So consistency has the same meaning that as the grid spacing h goes to 0, the local truncation error must go to 0. It's just that now we're looking at local truncation error as grid spacing, the spatial quantity goes to 0, as opposed to a time step for initial value problems. Okay, so there's a definition of consistency. That's exactly what you would expect based on what we know about it from initial value problems. Okay. I want to check here if there's anything from the text that I want to show you. Actually, no. Okay. Now, so since f is a function of three variables, x, y, and y prime, we would need to perform multivariable Taylor expansion around this center. So we're going to end up with partial derivatives of f with respect to x, y, and y prime in that Taylor expansion. We'll need to perform a Taylor expansion wherever y double prime pops up, because y is the exact solution, we know it's equal to this, so that needs to be taken into account. And so for this approach, and here I just chose two approaches to approximating y prime and y double prime. I could have used other finite difference formulas that would lead to their respective local truncation errors. So if I were to compute the local truncation error for this method, well, this would be equal to y double prime plus an error term, this error term, that's order h squared. This, when we do a multivariable Taylor expansion, the first term would be f of xi, y of xi, y prime of xi, which would cancel with a y double prime that came from here. Because this is second order accurate, then an error term would pop up from Taylor expanding this, that would also be order h squared. So this method turns out to be second order accurate. So if you were to actually work through the local truncation error, because your finite difference formulas, whatever order of accuracy they have, basically the minimum order of accuracy that they have, will end up being the order of accuracy of your overall method here. Turns out the multivariable Taylor expansion of this would actually be relatively simple because you're using a center, xi, y of xi, y prime of xi, but the first two of these are also where you're evaluating f. So in fact, any terms involving partial derivatives of f with respect to x or y, those terms would be 0. You'd only get terms, so it basically reduces to a single variable Taylor expansion around y prime of xi. What about stability? Recall that for initial value problems, the numerical method is stable if it can be proven that for any two solutions, any two computed solutions that the numerical method can generate, the difference between them over time is bounded by some constant times the difference in the initial data. Here we have an analogous definition that the numerical method is stable if the difference between any two computed solutions can be bounded in terms of the difference between their boundary data. So also, all these concepts of consistency, stability, convergence have the same relationship for boundary value problems as for initial value problems. That if a method is consistent and stable, then it is also convergent. That the difference between the computed and exact solution and any x value goes to 0 as h goes to 0. All right. As far as solution methods are concerned, so here we have a case of a linear boundary value problem. We saw this last time with a shooting method. But for convenience, I'm going to rewrite it this way. Everything involving y on one side, and everything not involving y on the other side. Then I replace the derivatives with finite difference formulas and get this. And then if I multiply through by h squared, and then group terms together based on the subscript of the y values. So in other words, I take all the terms involving yi minus 1, put them together, yi terms grouped together, yi plus 1 terms grouped together. So now my system of equations has this form. And this is for I going from 1 to n. But I have a boundary cases to think about. For instance, if I set I equal to 1 in here, then I'll have y1 here, y2 here, and y0 here. But that's a boundary value. That's equal to alpha. So then I have a y1 and y2 terms here. This part, if I replace y0 by alpha, then those terms need to be moved to the other side. So I include that over here. Similarly, for I equals n, we're at the right boundary now. I have yn plus 1, but that's equal to beta. So these terms, this part, in parentheses multiplied by beta, that has to be moved to the other side. We have that here. So really, if you use this equation for your interior points, so I going from 2 up to n minus 1. I equals 1, you have this. I equals n, you have this. So what you end up with can be described as a matrix vector product. So whatever quantities you have multiplying a y value, those are your matrix entries. So for example, this is the I entry. This is the entry in row I, column I minus 1. This is the entry in row I, column I plus 1. Those are no longer entries. So in other words, you have a system of linear equations, okay, ax equals b problem, but we write it as ay equals r, where y represents the solution, r represents all of your right-hand side terms, mainly this part, so minus h squared times your function r of x, and for the first and last equations, you have these boundary terms. The matrix A happens to be tridiagonal because the only entries in the matrix that are non-zero are because this is for row I, so we have II, that's a diagonal, row I, column I minus 1, that is the subdiagonal, and here we have row I, column I plus 1, that is the superdiagonal. So we have a tridiagonal matrix. It can be proven that if your function q of x is non-negative and h is sufficiently small, that the matrix is strictly row diagonally dominant. When you have a matrix that is strictly row diagonally dominant, it can be proven that it is guaranteed to be non-singular. And q should be non-negative. Recall that we're making the assumption that in your ODE, y double prime equals f. We're assuming that df dy is positive, and that would be q. So in that case, all you got to do is make sure that h is sufficiently small, and we can guarantee the system can be solved. Also, because the matrix is tridiagonal, solving the system of equations is very efficient. It only takes order n plus, as opposed to the usual order n cubed for solving a system of equations. I want to show you an example involving this. So it's an unshare and reshare. Okay. So for my text here, I have an example. So I'll show you the boundary value problems to be solved. Okay, so it's this one. This is the ODE. Solve the missile domain from 0 to 2. And here are our boundary conditions. So equals 0 at 0, equal to minus 4 at x equals 2. Okay. So how to solve that using finite differences. Okay, so first I have to find these function handles for the coefficients. So here P is a coefficient of y prime, Q is a coefficient of y, which is just equal to minus 1. So here we have constant coefficients in this case. But we want them to be vectors that have the same size as x. That's why I define it this way. Then a right-hand side function is x e to the x minus x. Note the dot star here, because I have to assume that x could possibly be a vector. So I want these function handles to be able to work regardless of whether the argument x is a number or a vector, or a matrix for that Here I specify my spatial domain, the interval AB, my boundary values alpha and beta. Here just choosing number of interior grid points, I'll just pick a small number, 10. This is a function that sets up and solves the system of equations. So James would be writing something like this. So I won't get into it here, but to see the data that's needed, the coefficients that define the ODE, the quantities that define the boundary conditions, and the number of grid points. So it would form the matrix A and the right-hand side vector R, and then, well, backslash, and then you'd have your solution. This is the exact solution. Tedious solving by hand process, like from Math 285. So I implement that here, just so I can check the accuracy of the solution. And what I do is, I want to plot two things side by side. So I use a subplot command that makes a 1x2 matrix of plots. And then I select the first plot, that's what the 1 is, the second 1 is for. And so here I plot my computed solution using a blue curve with diamonds for the data points. And then on the same plot, I plot, oh, that's weird, why did I do that? I make a comment that the exact and computed solutions are visually indistinguishable from one another. Yeah, because I plotted the computed solution twice. This is supposed to be exact. Well, why exact right here? Oh, God. Okay. All right. Oh, and these dots. I'm wondering, like, I know I've had this page here that has all the mistakes that have been found so far. But yeah, I did report this mistake. Okay. Yeah. Well, the error is small. So this is what's happened in the error plot. So using subplot 1, 2, 2, same matrix of plots, but the second plot is correct. Here I plot the error, y exact minus y, absolute value. And we see that so the error is on the order of 10 to the minus 3. So if I did plot correctly, I think it actually would produce something like this. I should check that though. If they ever let me put out a second edition, I will. Okay. Yeah, and of course, be sure to label your axes. Okay. So this is how you can specify a boundary value problem. But if you have a routine to obtain a computed solution, how you would visualize that. All right, yeah, so I'll have to make a note of that. Dang it. Okay. All right, any questions about solving a linear boundary value problem before I talk about nonlinear? All right. Now, for a nonlinear case, so we're still using the same finite difference approximations for y double prime and y prime. Now we just have a nonlinear system of equations to solve. So we value function, capital F of y, that has component functions that all must equal to 0 as a solution. So, and here are each of those component functions corresponding to the equations that we had before, just nonlinear instead of linear. So here we have the equation for the leftmost point, that would include the left boundary value alpha, and then for interior points, and for the rightmost point, where the right boundary value beta comes into play. So what you can do is use whatever iteration. So from one section I covered in chapter 11, systems of nonlinear equations. I covered fixed point, Newton's method, and also a quasi-Newton's method called Boyden's method. Here I'll just talk about Newton's method. So Newton's method for system of equations, here are the general formulas for it, that the new value is equal to a previous value plus this step. This step is obtained by solving this system of linear equations. Jacobian of f times your step equals minus the f value. So it's equivalent to minus f over f prime that we have in Newton's method for a single equation in chapter 10. So we need to compute this Jacobian matrix for this function f. So that means taking derivatives of all of these with respect to each of the components of y. That's how the Jacobian matrix is defined, taking a partial derivative of some component function of f with respect to some element of a vector y. Now, because of the finite differences here, the Jacobian matrix will turn out to be tridiagonal, just like the matrix from the linear case. So, for example, for diagonal entries, if I take a derivative of this equation, fi, y equals 0, with respect to yi, then here, these are different y values. Those will not contribute anything. Derivatives of those will be 0. But here I have minus 2 over h squared that shows up down here for multiple of yi. And then I look for where yi appears in here, only in the second argument. So I have derivative of f with respect to y times the derivative of this with respect to yi, and that's going to be 1. So this is these are my diagonal entries of my Jacobian. And I do the same thing for this case. I take a derivative of this with respect to y1, or this with respect to yn. I'll end up getting the same thing. So this applies for all I, going from 1 to n. But now if I take the derivative of this with respect to yi plus 1, well, this is the only term that'll contribute. I'll get a 1 over h squared, as you see here. And then I have minus, and then where does yi plus 1 appear? Right here. So I have minus partial of f with respect to y prime, the third argument of all this, and then take the derivative of this with respect to yi plus 1. That leads to the factor of 1 over 2h out here, and then this minus we also have here. So these are the superdiagonal entries of a Jacobian. And then similarly, if I take the derivative of this with respect to yi minus 1, I'll get a 1 over h squared from here, minus partial of f with respect to y prime, and then multiplied by minus 1 over 2h. That leads to this plus 1 over 2h down here. These are the subdiagonal entries of my Jacobian. And so if you derivative of these with respect to any other y, I would get 0, because no other element of y appears in this function. questions about how these were obtained? And here, for instance, let's suppose I equals 1. You know, y is 0 here. You just keep in mind to substitute alpha in that case. So now, we're almost ready to carry out Newton's method and solving a tridiagonal system. So at least that'll be efficient for each iteration. But we still need an initial guess. One simplistic idea for initial guess is this. All it is notice it doesn't involve a function f at all. It's nothing but a linear function. It's the line that passes through the points a alpha and b beta. At least it satisfies the boundary conditions. You should certainly use an initial guess that satisfies the boundary conditions. So as an example, here's my nonlinear ODE on the interval 1 to 2, my boundary values. This is my function f, that's just the right-hand side. So I need the derivatives of this with respect to y, which is right here, and then with respect to y prime, which is minus y. So in this case, I'm thinking of y and y prime as independent variables for purposes of this differentiation. So now, here I have my system of equations. For my discrete system. So here we have y double prime, finite difference formula. And then I have my function f, which is y cubed minus y prime, which is replaced by a finite difference formula, this center difference. Same thing here, except I have the appropriate boundary values filled in. And also here. Then I obtain a Jacobian. I am taking derivatives of this with respect to yi, or yi plus 1, or yi minus 1. And carrying out those differentiations, respectively, gives me all these equations here. And actually, the Jacobian turned out to have a fairly simple form. That just depends on the function f. So now I can make my initial guess, like something like this, for instance, and then use that Jacobian and that function f to carry out my Newton steps until I have convergence. Nothing to it.
I don't believe that.
Okay. Yeah, I guess I can let you be the judge.
Yeah.
Okay. Flip to an example. Wait. Okay, that is the same problem I was just talking about. Oh, but this has a, wait, that's a linear case. Wait, example 13.2.3. Oh, okay, this is what I want. So here we have a function whose job it is to evaluate this function. So really this function, capital F of y, in terms of these component functions. So what are the arguments? A vector of x values, a vector of corresponding y values, and then a function handle for f, a function from your ODE. That's a function of x, y, and y prime. And then the grid spacing h. So that's enough information to evaluate all of these. So how do I proceed with that? Now, the assumption here, very important, is assume that the vectors x and y coming in include boundary points. So x is not just interior points as well as x equals a at the first element, x equals b as the last element. Similarly, the vector y would have the alpha and beta boundary values as its first and last elements. But I do want the interior points for evaluating this. So I define my variable xi to be all elements of x except the first and last. Those are the interior x values, and then the corresponding y values. I also want to refer to y plus 1 wherever it occurs in my formulas. So that would be all values of y except the first two. And also yi minus 1 would be all y values except the last two. That way, and the way I've named this, yi plus 1. And here we have yi minus 1. That's the weird names that we have here. So now I have y plus 1 and yi minus 1. I can just use this finite difference formula. So now I have my approximate y prime values. And now I can evaluate f. So I have yi plus 1 minus 2yi plus yi minus 1, all for h squared, minus f at my interior x values, interior y values, and then my y prime values that are finite differences as a third argument to f. So now I've evaluated f. And I bring this up because, like, for a coding project, you need a similar function to evaluate the Jacobian. So similar expressions can be used for that. But for Jacobian, you would need the partial derivatives of f with respect to y and y prime also as function handles. But yeah, that's something else that the user would have to provide.
And I don't remember, but did you have H as a input, like a user input?
Oh, the number of grid points is an input.
Okay.
And from that you get H. Yeah. And in fact, so the code that I have that is supposed to run your methods does it for each problem runs with 100 grid points and then 200 grid points. So then what you can do is, since it's going to give you error, you can check, well, the finite difference method is second order accurate. So you should see the error decrease by a factor of roughly 4 to be sure that you have second order accuracy. And I think it has happened once in a while where I'll get your code and I go ahead and run my test code on it and look at the error and say like, well, it seems to be producing the right solution based on the plot, but there's something off about the order of accuracy. So something was wrong. If you were to use a different root finding method, so instead of Newton's method, if you use fixed point or secant, then of course you don't need derivatives. You would not need the derivative of little f with respect to y or y prime. So fewer inputs required. And I haven't got into it here, but okay. Oh, where is it? Oh. So you're trying to solve this system. If you write it in this form, y equals g of y, where this is your function g, which has rather unusual appearance. And it turns out that if h is chosen sufficiently small, and the parameter mu is chosen sufficiently large, then it can be proven that this fixed point iteration will converge. There's a reason why, I don't think I assigned, what did I assign from this section? Oh, okay, problems 1, 5, and 6. Yeah. You'd be glad I did not assign this one. Number one, that would have been fun. From a linear case, I believe. Oh, actually, for linear or nonlinear. This is a proof I dug out of a very old numerical analysis text by Keller. He wrote a whole book on 2-point boundary value problems. That to prove under the right circumstances that the finite difference scheme that I described is actually stable. Okay. And it is possible to prove that consistency and stability guarantee convergence, just like for initial value problems. Okay. Questions about anything? Or about the final other option? All right, well, that's it for the whole semester. I can have more time to struggle with whatever else you have going on. Yeah, let me know what you're going to do final scheduling wise. I mean, we have time. I guess 3 whole weeks to get everybody squared away. So as long as everything's in by May 12th.